Hello students, this is Rahmat Ali from Indirapuram Public School. Today we will discuss the chapter Laws of Motion. In this chapter we will discuss laws of motion, inertia, its types, law of conservation of linear momentum and its application in real life. We will start from inertia. Let us observe objects around us. Can this TV set in your room move on its own? Can any other object in your surrounding change its state? Answer is no. Do you know the reason behind it? Reason is inertia. What is inertia? It is the inherent property of a body due to which it cannot change its state. That means if a body is at rest, it remains at rest. If the body is in the state of motion, then it remains in motion. Inertia, it is measured in terms of mass. That means more is the mass, more will be the inertia. What are the different types of inertia? In real life, we have learned that there are three types of inertia. Number 1, inertia of rest. Number 2, inertia of motion. Number 3, inertia of direction. Let's study one by one. Number 1, inertia of rest. It says that if an object is at rest, it remains at rest and it opposes any change in the state of rest. For example, if you are sitting in a bus and suddenly driver moves the bus, then your lower body, as it is in the contact of bus, it remains at rest, but the upper body, which is also at rest initially, that will remain at rest. When the bus moves, then lower body moves in the forward direction and the upper body, which was at rest, that remains at rest, and as a result you move in the backward direction. Second type of inertia, that is inertia of motion. It says that if an object is in the state of motion, then it tries to remain in motion. Let's have a look at an example. Let's say you are standing in a moving bus. So your body is moving with the bus. Suddenly, if driver applies brakes, then your lower body, which was in the contact of bus, that slow down the upper body, which was in motion, that continues to be in motion. As a result, you may fall in the forward direction. This is the reason that you are advised to fasten the seat belt in the moving vehicle. Third type of inertia, that is inertia of direction. It says that any object which is moving in a straight line, it opposes any change in its direction. For example, an object is tied with the string and that is being wheeled on a circular path. If you release this string, then the body moves in a straight line. That means the body will not change its direction anymore. Now we will come to the Newton's laws of motion. The first law of motion, it introduces force, and the law states that every object remains in the state until and unless any external force acts on it. It means if we want to change the position of any object, we will have to apply force on it. If we want to change direction of motion, then also we will have to apply force. What is this force? Force, it is a push or pull which can change the state of the body. It is a vector quantity, its SI unit is Newton and its dimension is mLt minus 2. Now we will study linear momentum. It is the product of mass and its velocity. Velocity is a vector quantity, so the linear momentum is also a vector quantity. If we say we have an object of mass m, it is moving with velocity v, then the linear momentum is represented by the symbol p. So, p equals to m into v. its SI unit is kilogram meter per second and the dimension is mLt to the power minus 1. As we have learned, according to the first law of motion, if we want to change velocity of the body, then we have to apply force. So, by the application of force, linear momentum of the body will change. Now, how much force is required for any action? In order to calculate direction of force and its magnitude, Newton proposed his second law. It states that rate of change of linear momentum is directly proportional to the force applied on the body. Let we have a body of mass m moving with velocity v. So, at this instant linear momentum of the body is mv if force applied in the body is F and in small time delta t linear momentum changes by delta p, then rate of change of linear momentum is equals to delta p upon delta t. According to the second law, delta p upon delta t is directly proportional to the force applied on the object. That means, delta p upon delta t is directly proportional to F. Putting a coefficient of proportionality k, we get F equals to k delta p upon delta t. As p equals to m v, so substituting the value of p, we get F equals to k m delta v upon delta t. If linear momentum of the object changes uniformly, then F will be equals to k m into a. Here a is called acceleration. If we choose the system of units in such a way that k equals to 1, then F equals to m into a. As we know, acceleration is a vector quantity, force is also a vector quantity. So, if we resolve force into its rectangular components, then we can write F x, that means force along x axis will be equals to mass into acceleration along x axis. Mathematically, we can write F x equals to m a x. Similarly, we can write F y equals to m a y, F z equals to m a z. It means acceleration will be produced in the direction only in which force is applied. If force is acting along x axis, then acceleration will be along x axis. If force is along y axis, then acceleration will be along y axis. If force is along z axis, then acceleration will also be only along z axis. As F equals to ma, so F equals to m delta v upon delta t. If delta v upon delta t is constant, then F is directly proportional to the mass of the body. It means, if we have a heavy body and a light body moving with same velocity, then in order to stop them in same time, we have to apply more force on heavy body. For example, I have a truck and a bicycle. Both are moving with the same velocity and I have to stop them within the same time interval. Then I will have to apply more force on the truck. Now, if I say mass m and delta t are constant in any case, then force will be directly proportional to change in velocity. That means, if we want to move a given body by higher velocity within given time, then we have to apply more force. Let us have an example. Say I am having a bicycle. I want to move this bicycle in a given interval of time, say with velocity 5 meter per second. Then I will have to apply some force. If this time I will have to move this body with a velocity 10 meter per second in the same time, then I will have to apply comparatively larger force. As delta P upon delta T is directly proportional to F, then in the new case we will say delta P is constant. That means mass of the body and change in velocity both are constant. Then from the equation we get that force is inversely proportional to time. It means if you want to stop a given body moving with a given velocity within a shorter interval of time, then we will have to apply more force. In the similar way, lowering of the hands by the cricketer while taking a catch can be explained. As force is inversely proportional to time, so the cricketer lowers his hand while taking catch. Doing so, he is increasing the time period. As force is inversely proportional to time period, so he has to apply lesser force. Let us do a numerical based on the concept. Let V have a ball of mass m moving with velocity v. If the angle of incidence is 30 degree with the wall, after collision with the rigid surface, it reflects at same angle. We have to calculate change in linear momentum. Let us say mass of the body is m, velocity is v. As angle of incidence is 30 degree, so on resolving linear momentum into its rectangular components, we get Pi equals to mv cos 30 along I minus mv sin 30 along j. After collision, it bounces back at the same angle, so resolving linear momentum into its rectangular components, we get mv cos 30 degree along I plus mv sin 30 degree along j. So, change in linear momentum delta P equals to P final minus P initial. Substituting the values, we get delta P equals to 2 mv sin 30 along j. Substituting the value of sin 30, we get delta P equals to mv. Today, we have discussed first law of motion, inertia, its types. In the next episode, we will discuss impulse, Newton's third law, its real life based examples, law of conservation of linear momentum and its real life based examples, and many more phenomena based on it. Thank you.